Mm. All right. So, i- if we were um, talking about matter in the last class, then usually um, the topic that comes after that class is either having to do with physical and chemical changes um, in states of matter or in matter itself. Okay, so uh, I think it's even though you don't remember what you guys discussed in class, it's still okay to learn about this because it will help your understanding of matter. Okay, so if there's any concept that you don't understand, just let me know. Um, so the first thing that we'll be considering, uh, first concept we'll be considering today, is physical changes. Okay, with states of matter. So now that this means it could be a solid, it could be a liquid, it could be a gas, but what we're talking about is a physical change. Okay, so if that happens, what is it all about? So you can see the text I have right there. It says physical changes are about energy and states of matter. Okay, so look at the example there. The first example, it says when you step on a can and crush it, what you've done is basically a physical change. Why? Because nothing happened about the, the chemical composition of that object. It's still a can, it's still metal, it's still a metal, right? Though the shape
Mm.
has, but nothing changed about its state. Okay, of course, something changed about its shape. Okay, but the change in in its shape didn't talk about a change in its state or its chemical composition. So it's strictly a physical change. Another example, let's say you melt ice. Ice, you melt it and it, became water, right? Remember what we talked about in the last class. When you apply heat, ice would melt. Okay, that's a melting process. And then if you apply heat again, water, liquid water will become vapor, steam. Okay, so again, that still is a physical change. All right. Um, uh, in this case, there was, excuse me. Uh, there was a change, a physical change again, but it's still physical. So it's still water, right?
Mm-hmm.
All right. Um, then the last example we want to talk about is a sugar cube. If you put it in water, right, and drink the water or taste the water, you see that the water still tastes like sugar. So
Mm-hmm.
technically, it's still sugar that's there. The chemical composition of of what you put in the water to dissolve didn't change. So that means um, it's still a physical change. Now take note, physical changes don't involve a change in the chemical structure of what is involved. That's what you just need to remember. Now let's look at the next um, example, which should be chemical changes. I want you to see the difference now. Chemical changes happen on a molecular level. That's the first thing we need to understand. Things would actually shift. Okay, so they happen on a much smaller scale. and things that would show you that a chemical change has occurred. Of course, observe that you can observe with the human eye is would be like color changes. Okay, um, um, they happen at between molecules. Molecules can't be seen by the human eye, and yeah, even if you want to reduce that something has happened at the molecular level, it would have to be with a very powerful microscope. Okay, um, but the stuff would happen that would show us that a chemical change has occurred, and that's usually a color change. Okay, so look at a classical example. When iron rusts, okay, that Fe that you see in the bracket there, Fe is short for ferrous for iron is the chemical symbol for iron on the periodic table. Okay, so when iron rusts, you can see it happen over a long period of time. Okay, depending on its exposure to water in the atmosphere. Now, rust actually involves a change at the molecular level. Now you might be wondering what kind of change happens when iron rusts. Well, remember there's there's water vapor in the atmosphere, right? So if that water, under a given temperature, reacts with iron, okay, you now have another substance that's formed, and that's why, of course, in the presence of air too. So you need to also take note of that. So you now see that the actual molecules have changed. It's not just iron that you have. Formerly, before rust started, it was just iron. But when rust has started, when the process starts, it doesn't happen all at the same time. Take note. But iron will react with oxygen. So you now have something called oxide. Okay, so that's what that brownish, um, whenever you see iron that has started rusting, right, it has that brownish coating, showing that the iron is reacting with something and it has changed. So again, that is a chemical change. Why? Because it happens at the molecular level. Okay, so you need to understand that there are molecules, right? The smallest, um, um, what do you call it? Uh, uh, State or the smallest size that you can say a substance exists in is a molecule. Okay, of course, we know there's an atom, but usually most substances, atoms, two or more atoms will come together to form a molecule. Okay, so when they say
Yeah.
a molecule, you need to understand it could also be at the atomic level. Okay, all right. So I'm sure you've seen iron that rusts, right? Or that has rusted before. Have you?
No.
You haven't.
Pardon?
Have you seen iron rusting before? Have you?
Oh, yeah.
Okay. All right. All right. So you need to understand that it has changed, right? Now, you might be wondering, is there a physical way of knowing it has changed? Yes. If you look at iron that rusts, if you look at that picture that is in the on the slide there, you see it looks brownish. Okay. So number one, iron has this look, this silver-like look, right? But when it starts rusting, it's not really appealing. It doesn't look attractive. Brownish look. Okay. So you will know that it has started happening, right? But it happens at the molecular level. Now look at the second example there. Burning a sugar cube is a chemical change. Why? Now, I'm sure you're wondering, how is it a chemical change? There's energy from the fire that has broken down the chemical bond. Now, you might be wondering, what chemical bond? If you look at the structure of sugar, let me see if I can explain that. Uh, if I can use a diagram to explain that. Just give me a minute. Okay, so I'm going to share now. Okay. Okay. Can you still see my screen?
Mm-hmm.
Okay, good. All right. So I was trying to explain what happens when you burn sugar. I don't know if you've ever tried it before. Maybe in a lab. Well, not at home, of course. I don't expect you to try that at home. But have you ever seen it being done in a lab where they took a sugar cube and they put it on a Bunsen burner? You know, the gas, the
Yeah,
gas.
I think so. Yeah,
What did
yeah.
you? What happened?
It's it started turning like brownish.
Yeah. And if you keep doing it, it turns black, right?
Yeah.
Okay. Now, I want to just explain briefly. I'm not going to go into too many details, but I want to explain briefly what happens there and why it is a chemical change. Now, sugar usually the chemical composition of sugar usually looks like this. If you guys have, I'm not even sure if they will show you this that when you guys are discussing photosynthesis. So a sugar usually looks something like this. See, don't worry, I might, I'm just putting an emphasis on certain things. Okay, so don't let what I'm going to write now confuse you. I'm going to quickly explain it. Okay,
Mm-hmm.
now this is how a sugar basically looks. It's remember carbohydrates are also classed as sugars, right? Now, typically, a carbohydrate or a sugar looks like what I just wrote down on the screen. Okay,
Yeah.
C6H12O6. Okay, the C is carbon, the element carbon. The H, the element hydrogen, and the O is the element oxygen. Now, why did I show you this? Remember, again, I said I wanted to show you what's happening at the molecular level. Now, if you remember, water looks something like H2O. Am I right?
Yeah.
Good. Now, if you look very well at what you have there, H12O6 looks more like H2O that has um, six water molecules, together. If you look at it very well, that's actually what's happening. So the six, if you look at the six multiplied the two and it became 12. And also the six multiplied the one. You might not be able to see the one in the oxygen, but there's an imaginary one there. You know that happens in mathematics a lot, right? We always have imaginary one. Well, it also happens in chemistry or in science. Okay, so you have an imaginary one by that oxygen there. Now, when you multiply 6 by 2, you have 12. And when you multiply 6 by 1, you have what? 6. Now, I want you to see what's happening here carefully. So, technically, a sugar is simply carbon that combines with water. I don't know if you can see it simply in that form. If that is so, if that is the simplest way to describe a sugar, right? And there are bonds and all that, even though it looks whitish. Guess what? By the time you expose that sugar to heat, guess what is going to happen? All the water would leave. What do you think is going to happen next?
Not sure.
Well, imagine if I just said a sugar is simply carbon and water, and you apply heat, and the water leaves because water usually evaporates when you apply heat, right?
Mm-hmm.
Good. So if the water leaves, that means you are left with carbon, and carbon is usually blackish in nature. So that's really what's happening there. The water left. Okay. In other words, all the bonds between the carbon and the water molecules were all broken. Okay. And the water vaporized. turn to steam, okay, leaving you with carbon. And guess what? When carbon is alone, it can't hide. It turns black. Okay, that's the reason why you saw that color change. You know, when the sugar was heated in the lab. Okay, so I just felt I should just throw some light on that so that you'll be able to appreciate it better. Why is it that burning a sugar cube is a chemical change? It's a chemical change because the bond between the carbon and the water molecules gets broken. Okay, you know, and once a chemical bond is broken at that level, it definitely is a chemical change. Okay.
Yeah.
All right. So let's consider something else. Now let me give you another example of a chemical change. Now, do you realize that what happens in the kitchen at home every day is actually a chemical change? Well, you might not be sure what exactly is happening, but when you cook food, okay, when you cook food in the kitchen, guess what? And you're applying heat, you know, whatever food you're cooking, okay, there is definitely a chemical change. How do I know? Okay, so you will come to learn later that physical changes usually can be reversed. Usually, physical changes can be reversed. Okay, but guess what? Chemical changes cannot be reversed. Did you get that?
Yeah.
Okay. So so in other words, when you cook food, you've cooked it. Guess what? You can't the food can't, you know, if you started with onions, pepper and all that stuff, once the food is cooked, you can't even tell from the other. So there's no way you can make that food go back to what it was before. The onions and the pepper and the all the other ingredients that you used to cook it. But for physical changes like the ones that we talked about, sugar dissolving in water, what else? What other example did we talk about for physical changes? Let's go back. I just wanted to make that point so you'd remember. Okay, so we talked about melting, the dissolving sugar cube in water, melting ice cube, okay, ice becoming liquid because of applying heat. And then we also talked about crushing a can, okay. All these things can be reversed. Okay, take a look at them carefully. All of them can be reversed. How do you reverse melting an ice cube to become liquid? Simple. Remove the heat from it, put it in the freezer, and it freezes, right? It can become ice again. How do you dissolve? How do you reverse dissolving a sugar cube? Simple. Apply heat, and the water will do what? Evaporate and leave you with the sugar. The same thing applies to salt. Okay. All right. So let's go to um, the next concept. Here. So again, this is more like a uh, recreation of what is actually happening. Okay, states of matter. All right. Um, um, we have different states, which could also be called phases of matter. Right. Elements and compounds can move from one phase to another phase when physical forces are present. Of course, one of those forces which we have seen so far is temperature or application of heat. Okay. When temperature changes, states of matter can also change. Now, this is the general principle. When temperature rises or heat energy is absorbed from the environment or from another source, matter moves to a more active state. I want you to take note of that. They become more active. All right. They become more active. Okay. So I think we've said this that solids are usually packed, compact. Okay. Remember that. when solids are packed together, and the closer they are, the harder the substance. Okay, that's the reason why solids cannot, have that rigid shape. Okay. Um, I think this is really more like a recap of what we did in the last class. So the thing that we need to remember in this concept is that a solid has its own shape. It doesn't take the shape of another container that it's in, if it's in any container anyway. It just has its own shape. All right. And that's because it's compact. So it can have its own shape. Comparing them with liquids and gases. Liquids and gases, their molecules are bouncing and floating around. Why? Because remember, as you change from one state of matter to the next state, the molecules become more active. That means they become more freer to move, okay, where they want. Okay. Of course, you know by now that a gas, the molecules and the molecules in a gas are even way freer than the molecules in a liquid, right?
Mm-hmm.
Yeah. All right. So just that's more like a recap of it. Okay. So um there was a concept I wanted to mention to you last time. Maybe I'll talk about it today. That sometimes some substances can go from solid, instead of going from solid to liquid before they become gas, some substances can go straight from solid to gas. Um, and surprisingly, you may have even interacted with some of those substances. Okay, so um, um, what's the main characteristic of a liquid is the fact that it takes the shape of whatever container you place it in. Why? It's not as rigid and as hard as a solid. Okay, so one more concept which we didn't talk about last week in our last class here is that liquids are difficult to compress, unlike gases. Why? They are difficult to compress because even though they are freer to move, they are not so free. Okay, so you can't compress them. Okay, compressing something means that you can push it into a smaller space, and that you can achieve that more with a gas than a liquid. So um okay, so you can see some applications of liquid. Shock absorbers in cars, some of them compress liquid, even brakes. Okay, also the brakes in some cars also compress liquids. There's this what they call it. You would have noticed it. Used to raise a car. What they call that stuff again? Can't remember now. Um, So let me just give you a picture. I can't remember the name now. So let's say you had, you were in a car and the car had a flat tire, and you wanted to raise the car up, right, so that you could change the tires and all that. That's tool, right? It's if you look at most of them, if you look at them carefully, you see that they have like a cylinder, right, that contains a liquid. Okay, that liquid, the principle that that cylinder is working on to be able to raise the car up is, is because liquid cannot be compressed. Okay, so they try to, well, of course, they still maintain their volume, but that hard property of liquid being hard to compress helps the car to, go up when you are applying pressure, trying to lift the car up. Do you understand what I'm talking about?
Yeah.
Okay. I just seem to have forgotten the name. I don't know. And when I needed it most. Okay. So liquids have cohesive sticky forces at work. that hold the molecules together. Well, yes, that's technically why they are the way they are. All right, so that's it. Solid becomes liquid and liquid becomes gas. Okay, so of course these are the guys that are the freest to move around. Um, gases. We have that gases are spread out. I mean, there's nothing. The cohesive forces between gases are so negligible that it's as if they are non-existent. Okay, and of course, trust the molecules and the particles of a gas. They are full of energy, so they can move as far as they want. Okay, that makes gases unique. You can compress them, right? You can compress them to whatever shape you need them to be. And they can, of course, they also take the shape of any container that you put them in. But now, the fact that you can compress them means you can make them smaller than they are. That is also a desirable property where in some applications. Um, so we will not talk about gas or the pressure and all that, but that's the concept we probably discussed in a higher class. Okay, okay. So I'm trying to make sure that this is not something that um too above your. Okay, okay, okay. So I said I was going to talk about, right, where you have solid first becoming a liquid, and then a liquid before a liquid becomes a gas. Some substances do not follow that pattern. Okay, so I'm going to let me just say it at this point. Um, there's a substance that I can give you an example. You may have noticed it, right? If you go to a public toilet, right? The convenience in some places. You might even have noticed it in school. Where you have um wall um those like toilets that hang on the wall. Okay. I, I don't know if you know what I'm talking about. You would see that there are some pebbles, like colorful pebbles that they put in those things, and the idea is that they kind of give off a pleasant scent whenever water touches them, or well, urine, right, touches them. So the whole idea is that anything that heats them up a little, makes them to release a scent. Do you know what I'm talking about?
Yeah.
Okay. Now, those pebbles, right? Now they have a chemical name. I don't know which name you know them by, but most people have called them camphor. Okay. Now the chemical name for them is manganese. No, not magnesium, manganese oxide. Okay. So the whole idea of having those things there is that they are unique. They don't change from solid to liquid and then from liquid to gas. No, they go straight from solid to gas, and that's the reason why you even use them in restrooms. Okay, so the whole idea is whether you put them in a sink while you're washing your hands, as the water is hitting them, right, like touching them, they easily change from solid to gas, and that's why you can perceive that um nice scent they give off whenever you're in the restroom. So that's a way of kind of controlling odor um in a restroom, and it's called manganese oxide. Okay, that's the chemical name, and most people call it camphor. Um, maybe your mom might know what I'm talking about. In Nigeria, and yes, mostly if you've grown up in Nigeria, you'd also know about this. There was our mom would have those same pebbles inside their boxes, okay, where they keep their clothes and all that. And the whole idea was that no matter how long you shut the box, right, that contains those clothes, this is not these days of keeping clothes in a wardrobe. I'm talking about, some expensive wrapper materials that they would keep for long periods, and they will only wear them at certain parties or stuff like that. They will put them in a box. So, if you keep clothes too long an enclosed space, they will tend to smell, right?
Mm-hmm.
So what they do is they put those camphor inside those boxes. Why? So that if no matter how long they stay in those boxes, the moment you raise the lid, the camphor itself, some of it has already converted to what? Gas, right? And as it converted to gas there and it stays within that container, it gives the clothes inside that box a nice smell. All right. And it's actually pleasant. They look whitish in color. Some of them look whitish. These days they now have colors. You could see green, blue, red, stuff like that. They look colorful. But then we used to know them as just white. Okay. So like I said again, if you don't know what I'm talking about, it's okay. But I know that your mom will definitely know what I'm talking about. She will have an idea what I'm talking about. Um maybe no, I may have know what I'm talking about. Yeah. But yes. So again, that process of a solid becoming a gas straight off. Okay, it's a pleasant property because, like you see, I've told you different ways they've been used, either in the restroom or for keeping clothes. Having them, giving them a nice smell, no matter how long you keep them. For like if you're traveling on a journey or something, it's a good quality. Now, there's a name for that process. That's where I'm going. There's a name for that process. Okay, the name is, do you have your note with you?
No,
No, I mean our class note, not, I mean, I don't mean your science notebook from school. The one that you use in our classes. Your
no,
just,
I don't know, but
what happened? Is it lost? I hope it's not that it's lost.
I'm not sure where it is, but
Hmm. Okay. I think do you have a particular place you keep it? I think you should have a particular place you keep it so that whenever it's time for class, you would always have it handy, right?
yeah.
Okay, so I can't anyway. I don't know how now. I don't know how to do this now. Okay, I'll send you this thing I'm typing now on WhatsApp. But please, next time, always make sure you have your notebook with you and your writing material. Not just in maths classes. We could also take notes in our science classes. So I said I wanted to talk about a particular uh, the name of that process of a solid becoming a gas straight off. Okay, it's called sublimation. I'm typing it now on the screen. Sublimation. Okay, so that's the name of the process. So let me just write the meaning there. Sublimation means no, I think I should make it look like this. Sublimation is the process of, okay, it's the process where uh solid changes from uh changes to gas. Sorry, I meant to say it changes to gas. Um um Now, even application of heat. Now you might be thinking, well, is there really heat applied in those instances? I want you to always remember that no matter how negligible the heat uh, in an environment is, guess what? There's still heat there. Okay, so that's the meaning of sublimation. It's a process whereby solid changes to gas with an application of heat. And guess what? The reverse processes also happens when you reduce, when you remove the heat, the gas would go straight to solid. It doesn't become a liquid. It's a rare property. Okay, so do you have any questions on what I've explained so that I could quickly explain it before I move on to another concept? Do you have any?
No.
Okay. All right. So some of these things, like I said again, you will definitely talk about them in class. So don't um get phased out if it looks like, oh, you've not really understood it. But I try to make it as simple as possible so that you would be able to appreciate it better. Okay. So
Yeah.
the rest of this particular material is uh um it's talking about something that's a bit on the advanced side, right? So I'm not going to highlight it now. So let me move to another one that should give us something to work with. Yeah. Let's see. Okay, 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 okay. All right. Yes. Aha. Perfect. This diagram highlights what I was saying back then. Now, so just please take a look at this. This is a very simple diagram that will help you to capture the idea I just said. I wish I could screenshot this. Sorry, I wish I could screenshot this. Let me maybe that's what I'm going to do. I'm going to screenshot it and I'll paste it in WhatsApp just like this. Okay, please do your best to transfer it to your note, our own class science class notebook, not the one in school.
Yeah. Oh, we done this one in school. The this one, like this type of table. I done it in my book.
Right. Okay, okay, you remember, right?
Yeah.
Okay, good. All right. Now, did you guys talk about sublimation?
Um. Yeah.
Okay, good. All right. So, of course, I believe that you understand it better now, right? Solid
Yeah.
going straight all the way to gas. And then, of course, the reverse process is when a gas becomes solid. You can see that it has a name. I didn't give you the name earlier, but this is the name, deposition. Okay. So just the important thing to understand is from one direction to the other, heat or energy is absorbed. It's usually heat energy. And then, of course, in the reverse direction, energy is released. Okay. Melting is the opposite of freezing. Evaporation is the opposite of condensation, and you know, and all that. So you can tell, when one is going in what direction. Okay. Um. Uh. One more thing about, you remember when we talked about chemical change, right? We said that
Mhm.
a chemical change happens at what level? The molecular level. Do you remember when I said that?
I think so.
Okay. So it happens at the molecular level. Now, the another fact for you to take note of is the fact is this: a new substance always is formed through a chemical reaction. It can never be the same thing you started with. Take as an example when I talked about iron rusting, right? When iron rots, there's no way you can have the same iron that you started with. In fact, when if you use your finger to feel iron that rots, it quickly, you know, I don't know how to say it. It kind of turns into like a powder, right? Now we know that iron, you can't even bend some of them. Okay. But when it turns into that powdery form, you can almost like mess it up, like just dismiss it or just brush it away, right? That's because a new substance is formed. Okay. And guess what? Remember what we said. Usually, chemical reactions are not reversible. You can't reverse the changes that have happened because they happen at a molecular level. Okay. All right. So of course, this is just something extra about chemical changes. A new substance is formed. There's something called a precipitate. Okay. So a precipitate is simply stuff that comes out from the solution. It doesn't dissolve. It shows itself as part of the solution as something that didn't dissolve in the whole process. Of course, there are changes in temperature, right? And production of light. Sometimes you might see something that looks like an explosion happen, but not really an explosion kind of thing. Okay, but light would show that something popped. Okay, and then of course, change in color or odor. That's the smell. All right, the smell, you normally notice that the smell happens that shows that a new substance was um formed. Okay. Um, okay, so now this material talks about nuclear change, where it talks about fission and fusion. I not want you to really um consider this for now, but um maybe in future when you guys talk about um um radioactivity, right? Then you talk about what do you call it? Fusion and fission. I don't want to go into it. Okay, so these are some examples, practical examples again of chemical change, which we didn't discuss. Okay, so that you will properly appreciate it. When you burn paper and paper turns to ashes, okay, again, that's what is happening again. It's like a white paper, right, becomes ashes. The ashes also tells you something that carbon, remember, ashes are usually black in color, right?
Mm.
So carbon again is formed as a result of burning paper completely. Okay, it becomes ashes, and that's as a result of carbon. Another one, when milk curdles, okay, is also a chemical change. Something is either it's becoming what do you call it? It's under the action of microbes, okay, microorganisms that happens. Okay, so milk that curdles is not is sometimes most of the time not really fit to drink. Okay, of course we talked about physical change when ice becomes water. Um, um, if you consider fruit getting ripe, you can see that there's no way a fruit that gets ripe can be reversed, right? Do you agree with that?
Mhm.
Uh-huh.
Mhm.
That's a chemical change. Okay. There's no way it's a physical change. So anytime you look at certain things, you can tell straight off that they are either a chemical change or a physical change. Okay. So if you look at clay, when you use clay to form, when clay is they are used to form pots or stuff like that, is would you say that that's a physical or chemical change?
I'm not sure.
Okay, so now let's consider it. Did anything change? It's still clay, right?
Yeah.
If you, for instance, let's say after it got dry, right? You expose it to sunlight, it got dry and all that. It accidentally fell. Let's just pretend it accidentally fell on the ground. The core component of that clay, the core component of the cup that fell, is still clay, isn't it?
Yeah.
No chemical change happened at the molecular level. Therefore, it's safe for you to class it as what? A physical change. All right.
Mm,
Did you get that?
yeah.
Okay. All right. Let's look at some other. Of course, this is our guy. Metal that rust. You know, this is clearly what? A chemical change. Look at that. It's so clear, and it makes the metal look, you know, I don't know whether the right word to use is disgusting. Okay. But the whole idea is that it's because it's metal and it's not been, it was not protected. Okay. So now let me see if you understand what I'm saying. What's the best way to protect metal from rust? What's the best way to protect it?
Um, is it like one of those sprays?
Yes, painting. Painting, that's the idea. Whether it's a spray or a brush. Okay. So we
Mm.
we we protect it by painting it. Yes. So it's that paint, basically, paint would simply do what? Create a layer above, between the ion and the atmosphere. So that prevents any chemical reaction from happening between the ion and air in the presence of water in the atmosphere. Yes, you're correct. So you called it a spray, so you can look at it in that fashion. Okay. All right. Let's look at this. Something called a silver tarnish. Okay. So I don't know if you've seen this happening before, but some metals that don't look classy, they don't look appealing at all. Okay. There's something called, should I say electrolysis, electroplating? Yeah, that's the word, electroplating. So they use that process to give it a fine finish. Okay. Just it takes a while, but it comes out. Now I want you to look at the spoon on the left hand side and the one on the right. It was formerly looking like the one on the right, but when they apply the silver, um if you apply that electroplating, the one on the right can look like the one on the left. Now, on the other hand, right, silver itself can also deteriorate, you know, and the one on the left can now look like the one on the right. Okay. Now, if you consider what's really happening there, in both cases, it's a chemical change. Why? Because something happens to the silver, just like the iron, that's similar to a rust. Okay, it reacted with something in the atmosphere. Did you get that?
Mm-hmm.
Okay, all right. Do you have any questions? I'm just basically taking you through examples of chemical changes and physical changes so that you you get the idea um, um, fully. Do you have any questions?
No.
Okay. All right. So I think, yeah. Okay. That is for this one. Now, if you remember, when I was talking about um, chemical changes, right? There was,
Mhm.
let me see. Yes, that's it. If you look at number three says changes in temperature. Changes in temperature. Now you might be wondering, is it the temperature from the gas that in that that's happening, or what? Now sometimes um it may be that, at some other times it may be something totally different, right? Um there are two basic ways.
Oh shit.
Sorry, you have a code.
Yeah.
Sorry about that. Okay, so there might be changes in temperature that would involve the experiment absorbing heat. Okay, sorry, the experiment absorbing heat from the atmosphere, and in other cases, the experiment gives off heat. Okay, so like I said, um, that's some detail I mean not really going to, except if you guys cover it in class, then I'll probably explain it in detail. But that is what um that is also covered in the concept about changes in temperature.
Mhm.
Okay, in a chemical system where um things are happening, where things are reacting. All right. Okay. So I just want to see if I have one more here that we can discuss before we call it a day. I don't really have much power on my laptop, but let's see how far we go. Okay. All right. So this is basically talking about physical properties of matter that you can observe. Okay. So um we talked about color. Okay, those are things that you can observe. Um Order, okay, and stuff like that. So um let's just quickly look at some physical properties of matter, right? We know the different forms that matter can exist. And if you talk about matter, matter is basically anything that occupies space, right? Has weight, occupies space. Okay, solid, liquid, gas, or plasma. Plasma looks like a combination of liquid and gas. It's somewhere in between, right? So it's not like uh gas or liquid. You can't put it in gas, you can't put it in liquid. So an example of plasma is what you have whenever rain falls, which is lightning. Okay. So some the first one we talk about here is malleability. Now malleability means it can be, you can see it there, the ability to be pounded into thin sheets. And that's a property of, like metals mostly. And that's how you see aluminum foil is is created. That's malleability. It can bend, and that property is a property of metals. That metals are easily, some of them, not all of them, they can bend easily. Okay. The next one here is ductility, and that is ability to be drawn into thin wires, and that's how electric wires are created. Okay, copper is a very good example. Did you say something, Mason?
No.
Okay, all right, all right. So the next property we could talk about, which I'm sure you appreciate, is solubility for physical substances. It can dissolve into another substance. You know, because when sugar dissolves in water or in coffee, stuff like that. All those things are um, um, the ability of a substance to dissolve into another substance. Of course, the substance that dissolves is called a solid, and the one that is dissolved in is called a solvent. Solid dissolves in a solvent to form a solution.
Mm.
Okay,
Mm.
all right. I'm sure you know about density, right? Do you have an idea of density? Hello, Mason.
Help him. You can't see him. You can't see him. He's not gonna bite you.
Mason, are you there?
Oh.
Yeah, I'm not feeling well.
Oh,
Maybe
sorry.
just one for today.
Okay, don't worry. We're almost done.
But
This is
I need to sleep because I'm not feeling well.
okay. It's fine. Maybe we'll continue in the next class. It's fine.
Oh,
Can you talk to him nicely?
okay.
All right.
Sorry.
It's okay. It's fine. Just try and get some rest as much as possible.
Yeah.
Okay.
Okay. Thank you, sir.
Well,
Have a good weekend.
all right. You too.